Assalamualaikum. My name is Muhammad Daniel Aikal bin Ahmad Sanan. My group we will present chapter 3, which is Sustainable Engineering Technology. I will be covering the introduction and two of its subtopics, which are the engineering technology in society and industrial revolution. Before we proceed to the introduction, let's take a look and overview of sustainable engineering.
With the beginning of industrialization, a new age of opportunities began. We started to produce more and better products than at any point before in human history. We discovered electricity and harvested nature's resources to help us improve our cities and production facilities. But as everything in life, the advancement came with a cost. The rapid improvements in the fields of mass production and technical advancements took its toll on the environment as well as life on Earth. More production means more energy consumption. More energy consumption means more demand for resources, which in turn leads to more waste. But it's not too late to escape the vicious circle and ensure that our technical advancements do not turn against us. Through the adoption of energy-efficient measures, overall industrial energy consumption can be cut by 25%, while global CO2 emissions can decrease by 12.4% by the year 2030. This will lead to a cut of 8% of the total global energy use. One solution for improving our environmental footprint is through the implementation of a circular economy. Less energy use will lead to reduced material losses, reduced solid waste, and a decrease of our water use. This will not only help the environment, but help us also improve production capacities and competitiveness. UNIDO's goal of achieving inclusive and sustainable industrial development is explicitly recognized and anchored within the 2030 Agenda. In particular, Sustainable Development Goal 9, Industry, Innovation and Infrastructure. At the same time, UNIDO contributes to the achievement of various other SDGs, such as SDG 7, Affordable and Clean Energy. UNIDO's services in safeguarding the environment include the promotion of sustainable waste management, national cleaner production centres, smart cities and eco-industrial parks, where the waste of one company becomes the resource for another. UNIDO's energy strategy is built around these areas: industrial energy efficiency, renewable energy as well as climate policy and networks. Over the years, we have implemented projects all over the world, projects which promote the achievement of inclusive and sustainable industrial development as enshrined in UNIDO's mandate, specifically in the CIS region, and with the support of the Russian Federation, we have implemented projects such as those which aim to enhance the technical capacities of CIS countries to address climate change in the region, or projects which support the industrial upgrading of the automotive supplier industry in Belarus, or projects which aim to build capacity for the environmentally safe management of potentially hazardous consumer products and industrial waste, or projects which aim to promote innovative and low-cost sustainable manufacturing technologies in the Kyrgyz Republic. We helped improve the competitiveness of export-oriented industries in Armenia through modernization and market access. Together with our partners, we call for collective actions and catalyze local and international developmental partners to provide the necessary support, knowledge, and financial resources needed for inclusive and sustainable industrial development. With our partners, we are currently implementing over 850 projects worldwide. But we won't stop there. We will fight for the advancement of economic competitiveness, the creation of shared prosperity, and the safeguarding of the environment. Our future starts now. You can help us to make it better.
So, what is sustainable engineering? Sustainable engineering is process of designing or operating systems such that they are use energy and resources sustainable. In other words, at a rate that does not compromise the natural environment or the ability of future generations to meet their own needs. Basically, it is safe. No pollution, no harming anything unreasonable. Next, we proceed to sustainable design. Every engineering discipline is engaged in sustainable design, employing numerous initiatives, especially life cycle analysis (LCA), pollution prevention, design for the environment (DFE), design for the assembly (DFD), and design for recycling (DFR). Firstly, what is LCA all about? LCA is used to assess environmental impacts associated with all stages of a product life. The stages include raw materials extraction, manufacturing the product, distribution via transportation, utilization, reuse and disposal, and recycling during the product's end of life. This kind of assessment is used by companies and product designers to better understand their product's impact, discover where the product can be improved, and work toward implementing those improvements. Next is design for the environment (DFE). DFE provides organizations with a practical method to minimize environmental impacts in an effort to create a more sustainable world. DFE practice maintains or improves product quality and cost while reducing environmental impacts. Next is design for disassemble (DFD). DFD is process to easily deassemble products for reuse and recycle materials from product assemblies after they have been disassembled. Let's take a look in more detail about DFD. For the example, mirror chair by Herman Miller, designed to be easily deassembled, returned to factory and can be deassembled in less than 15 minutes. 96% of chair is recyclable. As example, fabric turned into compost and plastic and molded plastic sheet bag recycled and remodeled into a new one. Lastly is design for recycling. DFR is design process on the recyclable of product at their end of life. For example, Dell's Latitude 5590 and 5285. In 2018, Design for Recycling DFR Award winner by Institute of Scrap Recycling Industry ISRI. All Dell Latitude notebooks are designed to be more than 97% recyclable. Latitude 5590 contains a modular design, making it easier to access and disassemble, such as removable battery and use standard fasteners. Latitude 5285 using gold recycled from used electronic products. This picture shows Dell's closed-loop system puts plastic from old computers into new ones. Firstly, computers are taken apart at Dell in Texas. Then plastic are shipped to Asia and metals are sold as commodities. In Asia, plastic is shredded, melted and mixed with virgin plastic. The 35% recycled material then goes into new components. The components go back to Dell where they use in new computers. Next we go to pollution control paradigm. What is cap and trade? Cap and trade is market-based approach to controlling pollution by providing economic incentive for reducing the emission of pollutants. So how it works? Cap is for the maximum amount of greenhouse gases (GHG) of a factory can produce. Each factory are given permits. Permits allow the factory to produce a certain amount of pollutants. So, if a factory is able to reduce the amount of pollutant or emission of GHG, they don't need to use some of their permits. This is where the trade is take place. They can sell their permits to any other factory that needs it because they produce more pollutants. This allows the overall emission to decrease. Let's take a look what is cap and trade.
As the name suggests, a cap and trade system has two parts. The first part is the cap. The government sets a maximum amount of emissions. The second part is the trade. The government sells or issues permits to emitters of greenhouse gases, and every emitter needs a permit for every ton of GHGs that they emit. The trade part is that they can trade among themselves, and in that market for permits, a price is established. Facing that carbon price, everyone has an incentive to reduce emissions. Let's look at an example. Imagine two companies. Let's call them Company A and Company B. Based on the market price of carbon, Company A and B determine what investments they can make that will reduce their emissions at a lower cost than paying the carbon price. They then must ensure their permits equal their remaining emissions. Company A identified many low-cost opportunities to reduce emissions. As a result, it has more permits than it needs. Company B, on the other hand, mostly has expensive options for reducing GHG emissions. As a result, it wants to buy additional permits. Trading benefits both companies. A sells its excess permits to B. What is the overall impact on the economy? All companies take actions that make sense for them. Collectively, their decisions satisfy the cap, with the low-cost firms doing more emissions reductions and the high-cost firms doing less. The overall impact is that emissions get reduced at the lowest possible economic cost.
Next, we proceed to green engineering. Green engineering is design, commercialization, and use of processes and products in a way that reduces pollution, promotes sustainability, and minimizes risk to human health and the environment without sacrificing economic viability and efficiency. The goals of green engineering are waste reduction, pollution prevention, materials management, and product enhancement. Next, we go to principle of engineering. Green engineering processes and products holistically use system analysis and integrate environmental impact assessment tools, conserve and improve natural ecosystems while protecting human health and well-being. Use life cycle thinking in all engineering activities. Ensure that all material and energy inputs and outputs are as inherently safe as possible. Minimize depletion of natural resources. Strive to prevent waste. Develop and apply engineering solutions. Actively engage communities and stakeholders in the development of engineering solutions. So what is the example of green engineering? Net zero buildings is one of the examples of green engineering. It is operate entirely on renewable sources of energy, designed to independently use renewable energy for the building's electricity and heating, ventilation, and air conditioning HVAC needs. It also able to generate the exact amount of energy needed for the site, so there is no energy waste. Next, we proceed to sustainable engineering framework. Firstly is traditional and sustainable approaches in engineering. These are the aspects to differentiate between traditional and sustainable approaches in engineering. Traditional engineering, they considers the object or process, focuses on technical issues, solve the immediate problem, considers the local context, assumes others will deal with political, ethical, and societal issues, while sustainable engineering, they will consider the whole system in which the object or process will be used, considers both technical and non-technical issues synergistically, strive to solve the problem for infinite future, considers the global context, and lastly, acknowledges the need to interact with experts in other disciplines related to the problem. Firstly, we go to the traditional engineering. Traditional engineering requires to solve problems that are presented with the best of their knowledge, within constraints of the approval authorities, and within schedule and financial constraints. Engineers search for methods that maximize function and minimize cost to clients. Next, we go to sustainable engineering. Sustainable engineering maximizes social benefit while minimizing ecological impact. In terms of social effect are community activities and employment rates. In terms of economic activities are business growth, employment rates, and inflation. Lastly, in terms of environmental effect are environmental contamination and endangered wildlife. So, what is the example of these two? In order to design an IT infrastructure, the traditional engineer will focus on performance while sustainable engineer will focus how will widespread use impact electricity demand and electronics recycling. Second is principle of sustainable engineering. This triangle figure lists the various principles of sustainable engineering versus environment, society, and economy. Some of these principles clearly gravitate towards one of the corners of this triangle and thus address particularly society, environment, and economic concerns. But some others, which are placed along the sides of the triangle, have connection to two of the poles of the diagram and address both society and economy, or both economy and environmental concern in some proportion. Those principles, placed in the center of the diagram, combine all three aspects of the sustainability to a certain degree, and hence their implementation would benefit all society, environment, and economic stakeholders. Next, we proceed to engineering technology in society. Engineering, science, and technology are influenced by society. Our human values, needs, or problems often determine what questions scientists investigate and what problems engineers tackle. Meanwhile, the technologies that are the products of science and engineering influence society and change human culture. As example, the impacts of cars and cell phones. People tend to think of engineering, science, and technology are three separate things. Actually, they are closely connected. For example, scientists use the technologies that engineers create to conduct their research. And when engineers start to design a new technology, they will use the scientific knowledge that have been developed by scientists. This is how engineering, science, and technology connect to and influence each other. In addition, you guys can search for Center for Human Technology www.humantech.com through website to see how actually the technology change our human culture. And lastly is Industrial Revolution. First revolution started in 1700s where water and steam power are used to mechanize production. Second revolution used electrical power to create mass production. Third revolution used electronics and IT to automate production. And fourth revolution will take what was started in the third with the adoption of computers and automation and enhance it with smart and autonomous systems fueled by data and machine learning. Last year, the fifth revolution has been proposed in Osaka. Next, we go to engineer in IR form. Engineering specialists in materials, biochemical, nanotech, and robotics will become critically important to the industry by 2020. Industry 4.0 describes the growing trend towards automation and data exchange in technology and processes within the manufacturing industry, including artificial intelligence (AI), Internet of Things (IoT), robotics, 3D printing, and autonomous vehicles. There are four major technologies driving Industry 4.0 that engineers need to know. First is additive manufacturing, second IoT, third big data and analytics, and fourth is autonomous robotics. Let's go to the four major technology. The first one is additive manufacturing. Additive manufacturing is also known as 3D printing. The engineer will use computer-aided design (CAD) or 3D object scanners. Additive manufacturing allows for the creation of objects with precise geometric shapes, layer upon layer. 3D printing is now used across a wide range of industries. The benefits of additive manufacturing are allow for more complicated design but also reduce the amount of raw materials used, lower labor costs and increase the potential for customized design in small batches. 3D printing become more mainstream and viable for use in mass production, especially with new advancements in metal manufacturing. Discovery of a revolutionary reversible 4D printing process make knowledge in this field more applicable to engineers. Let's see what is 3D printing and 4D printing all about.
What is additive manufacturing? Additive manufacturing, also known as 3D printing, is a process that creates a physical object from a digital design. An engineer designs the object using computer-aided design, or CAD software. The 3D design file is then sliced into thin layers and uploaded to an additive manufacturing machine. The manufacturing process begins once an extremely thin layer of metal powder is spread across the platform. A heat source, such as laser or electron beam, then melts the first layer of the 3D design. The platform is lowered, and another layer of metal powder is spread across the platform. The layering and melting process is then repeated until the part is complete. The metallic powder is removed, and a physical object is revealed. Additive manufacturing allows you to produce parts that are lighter, stronger, and more durable than traditionally made parts. Build times are faster. Engineers can add precise features and complex geometries without increasing cost. In fact, additive manufacturing is revolutionizing the way we work.
In a nutshell, 4D printing refers to 3D printed objects that have the ability to reshape or self-assemble over time. Now, we recognise that's quite a complicated nutshell to get your head around, so here's a bit more detail. 4D printing was born out of the self-assembly lab established by Skylar Tibbets at the Massachusetts Institute of Technology, or MIT. It was a concept he developed alongside Stratasys and Autodesk. It involves strategically positioning rigid and expandable materials next to each other within one 3D printed components. When the expandable materials come into contact with water, they grow up to 200% of their original volume, changing their shape and effectively repositioning the rigid materials either side of them. The expandable materials effectively create joints in the components that are activated in certain conditions, causing the entire component to adopt a different form. Depending on the expandable material used, the contact substance necessary for it to change shape could be water, or it could be heat, light, or a range of other simple energy inputs. Software enables components to be programmed on screen before they are created, and for that data to have effectively been programmed into the component once it's been created. Going beyond this range of small-scale demonstration pieces, it's thought the technology could be used in some form of self-repairing water pipes, in pipework that changes size in relation to water flow, or in hot and cold temperature water valves. Beyond plumbing, it also has potential in medicine, clothing and footwear that adapts to climatic conditions, or in childcare products that respond to temperature changes. If you enjoyed this video and would like to get more from the definitive video channel for construction, subscribe to the B1M.
Next, we go to IoT. IoT is a giant network of devices and objects with the ability to transfer data over a network in real time, without the need for human-to-human or human-to-computer interaction. One of the driving forces of IR4, helping organizations and businesses stay connected even across remote distances, monitor assets remotely to obtain insights, optimize processes across the entire value chain in a split second, and even innovate new business models with all the data that have been obtained. Over half of major new business processes and systems have been projected to incorporate IoT elements by year alone. It is engineers who will be relied on to create the platform, software, and hardware. Google Home is one of the examples of IoT. Now, let's take a look video about IoT.
The Internet of Things is changing much about the world we live in. from the way we drive to how we make purchases, and even how we get energy for our homes. Sophisticated sensors and chips are embedded in the physical things that surround us, each transmitting valuable data that lets us better understand how these things work and work together. But how exactly do all these devices share such large quantities of data? And how do we put that information to work? Whether we're improving the production of a factory, giving city residents real-time updates on where to park, or monitoring our personal health, it's the common Internet of Things platform that brings this diverse information together and provides the common language for the devices and apps to communicate with each other. The process starts with the devices themselves, which securely communicate with an Internet of Things platform. This platform integrates the data from many devices and applies analytics to share the most valuable data with applications that address industry-specific needs. Let's start with a simple example, a car. After taking a long road trip, Rebecca notices that her check engine light has come on. She knows that she needs to have her car looked at by a mechanic, but is not sure whether it's something minor or something that needs immediate attention. As it turns out, the sensor that triggered Rebecca's check engine light monitors the pressure in her brake line. This sensor is one of many monitoring processes throughout the car, which are constantly communicating with each other. A component in the car called the diagnostic bus gathers the data from all these sensors, then passes it to a gateway in the car. The gateway integrates and sorts the data from the sensors. This way, only the most relevant diagnostic information will be transmitted to the manufacturer's platform. But before sending this organized data, the car's gateway and platform must first register with each other and confirm a secure communication. The platform is constantly gathering and storing thousands of bits of information from Rebecca's car and hundreds of thousands of cars like hers, building an historical record in a secure database. The manufacturer has added rules and logic to the platform. So when Rebecca's car sends a signal that her brake fluid has dropped below a recommended level, the platform triggers an alert in her car. The manufacturer also uses the platform to create and manage applications that solve specific issues. In this case, the manufacturer can deploy an application on the platform called the Asset Management System. This application oversees all of their customers' cars on the road, as well as all the parts in their warehouses. It uses the data from Rebecca's car to offer her a potential appointment time to service her car, directions to the nearest certified dealer, and a coupon for the service. What's more, the app will ensure that Rebecca's brakes are covered under her warranty, that the correct replacement part is ordered, and then sent to the dealership so it is ready when she arrives. But the manufacturer's analysis does not stop there. They have also deployed a continuous engineering application that tracks not only Rebecca's car, but hundreds of thousands of others, looking for ways to improve the design and manufacturing process of the car itself. If the same problem in her brake line crops up in a critical number of other cars, the manufacturer uses applications custom-built for the automobile industry to pinpoint the exact problem. They can see if these cars were made at the same factory, used the same parts, or came off the assembly line on the same day. So what do all these pieces add up to? Streamlined inventory management for the dealer, a better, safer car from the manufacturer. And for Rebecca, it means she can be back on the road faster and get to where she's going safely. All thanks to the Internet of Things.
Next, we go to Big Data and Analytics. Digital ecosystem of Industry 4.0 will run on vast amounts of data as the number of sensors, embedded systems, as well as connected devices increase. To fully maximize this resource, organizations will first need talented data engineers who are capable of developing, constructing, optimizing, and managing both data storage architecture and data distribution. Engineers require technical knowledge in data structure and algorithm, data modeling, as well as data mining or warehousing. Engineers who are proficient in programming languages, query languages, and big data tools will be extremely important. It is not necessary for data engineers to do the job, but other engineering disciplines can do the job as long as they have certain certificate in big data and analytics. Next, take a look at a video about big data and analytics.
"90% of the data available in the world today has been created over the last 2 years. We find ourselves in the age of big data, but what does this mean exactly? Big data analytics is the study of huge amounts of stored data in order to extract behavior patterns. These data are characterized by the high speed they are being generated with, the huge volume they represent, the immense variety of typologies they encompass, and the degree of veracity they own. More than 2.5 trillion bytes of information are generated every day through our smartphones, tablets, GPS devices, sensors spread all over our cities, bank cards. What can be done with all this information? This is where big data analytics comes into play, a combination of high technology systems and mathematics which together are capable of analyzing all that information and providing it with a meaning of great value for companies or governments. There are 4 types of big data analytics. The descriptive one explains what happened in the past based on data presented through graphics or reports, but not why or what will happen in the future. The diagnostic one, closely linked to the previous type, seeks to understand the reasons why any given event took place in the past. The predictive one, the most useful for companies, goes through data in order to predict what could happen. And finally, the prescriptive one, an evolution of the preceding approach based on automation processing or A/B testing. This system, besides analyzing and predicting data, advises on how to proceed according to them by recommending, for example, the best location on your site to place a banner, or the most convenient gas station along your way if you want to avoid traffic. Big data analytics helps companies or public administrations to understand their users better, find previously unnoticeable opportunities, provide a better service, and even mitigate fraud. The revolution of datafication is just beginning.
Lastly is autonomous robot. Autonomous robot is intelligent machines capable of performing tasks in the world by themselves, without explicit human control. Intelligent machines refer to a robot that have been programmed by engineers to perform the task. Benefits of autonomous robot are it helps to reduce the risk of employee injury in dangerous environments, reduce failure rates, and improve speed and accuracy of routine operation. Engineers that can design and develop this industrial robot will be in high demand. Practical experience in automation technologies and their applications will also be advantageous. Autonomous vacuum is one of the examples of autonomous robot. Referring to this picture produced by Mari, robots have been used in the automotive industry for more than half a century. Robots operate side by side with humans to improve manufacturing capabilities. Usually, AGV, Automated Guided Vehicle, or AMR, Autonomous Mobility Robot, are used in this industry. Before I ending my presentation, let's take a look at 16 inventions of sustainable engineering technology. Okay, that's it for me, and thank you for watching.